I'm in the Adelaide Hills at Vista, and beneath me is the dry gully of what is actually the St Agnes Creek, which is alongside the pipeline coming down from Nancy's Hill. This pipeline is the Mannum to Adelaide pipeline, which is going down to the micro hydro plant at Hope Valley on Grand Junction Road. As a little exercise, let's see how we can start our own hydroelectricity company. So the first thing is to work out at a desk what the income is. When it comes to the calculation of how much energy we can get from a body of water in a hydro system, the first thing we have to consider is how much water there is, and secondly, what height the water is located at. In the metric system, 1 litre of water weighs 1 kilogram. Now this is 3 litres of water, so it weighs 3 kilograms. The question is how much energy is in this water. At the moment, I've lifted it up off the ground and it's just about 1 metre off the ground. So the three things we've got are height, volume, or weight, and gravity. And gravity is just over 9 meters per second, and if we move something up and down 1 meter every second, as I'm doing now, 1 meter, 3 kilograms times by 9 is 27. So I'm creating 27 watts of energy, which is enough to run a LED light globe. So it's simple. All you need to know is the volume, and if you measure it in litres, that is kilograms. Now when it comes to bigger volumes, they often talk about cubic meters. Now a cubic meter is actually 1,000 kilograms, 1,000 litres. Therefore it's really what's called a metric tonne. So let's look at some calculations for various existing hydro systems in the world. This is the formula for hydroelectricity. In the metric system, 1 litre of water weighs 1 kilogram, and in the video I use 3 kilograms or 3 litres of water, and gravity is a fixed constant of acceleration of 9.81 meters per second every second acceleration, and I lifted and lowered the water 1 meter in demonstration. So with a normal efficiency 0.8, that will produce 24 watts of energy. When you raise it up, you are turning the energy of my arm into positional energy of 24 watts, and when it's lowered, the 24 watts of energy is released, and what's happened is turned into heat because it's not being used. Here I'll rearrange the formula, and what we're trying to find out is how much water we need to have in our reservoir to create a hydro system for 1 gigawatts. And the extreme case here of 600 metre high head would require 764 litres of water in total, or 0.765 gigalitres of water if we wanted to run for 1 hour. But the reality is we'd be running this for 8 hours, and so we'd require 6 gigalitres of water. If we change this height to say 300 metres, we need 12 gigalitres of water. So by this rearranging the formula, we can find how much water we need to put into our 2 dams in a pumped hydro system to create a known amount of energy, using, in this case, 4 turbines of 250 megawatts to give us a total of 8 gigawatt hours of energy. So the theory of pumped hydro is that when the sun is shining, energy is being created by solar panels as an example, and it's used to pump water up the hill. Then when the sun goes down and there's no sun, then the water runs down the hill and the generators create electricity, and that cycle occurs over and over again. I'm in Happy Valley, South Australia in January, and at the moment it's 41 degrees temperature, and behind me is the Happy Valley Reservoir, built in the 1890s by the South Australian colonial government. The idea was that water was precious and the Onkaparinga River is on the other side of a mountain. So if they built a tunnel from a diversion dam on the Onkaparinga River, they could bring water here, and this is high enough to be able to use gravity to feed the suburbs around. The point of coming here is that the volume of this is 11.5 gigalitres of water. Compare this with the Presenzano pumped hydro system, which is using 6 gigalitres. So the volume of this reservoir, built in the 1890s with this earth dam, basically a turkey's nest dam, is twice the size of Presenzano. And we can see the environment around this is very pleasant. In fact, now this area is a public park. Let's look at this example of a closed loop pump hydro system which doesn't exist, which might exist in the Flinders Ranges of South Australia. Above the plains below is a reservoir with a penstock just by the escarpment down into the plains, and the level of the dam is such the penstock could get water by gravity to the start of the descent, and the head at that point is 395 metres down to the lower dam, which doesn't exist. And these two dams are being built using turkey's nest technology, where the dirt in the middle is moved out to create the walls on the plain, and in the case of the valley on top of the hill, the dirt at the back of the valley is brought forward to create a wall. And the length of the penstock is 3.6 kilometres. The key question here is how much water should be in these two dams, because this is a closed loop system, and we know that the head is 395 metres. So this is our fictional pumped hydro system called Mount Brown, and here is the equation for hydro, QGHE equals P. And here we're using the 11.5 gigalitres of water, which is currently in Happy Valley Reservoir since 1890. And I have discovered that if we're using 250 watt turbines, then we need 5 turbines for this to work. If we have all the water running out in 8 hours. If we want to run it for a shorter period of time, say 4 hours, then we can't run all the water out. We can only have 50% of the water running out to get us back to a stable result. So we can see then with our formula, if we go back to the full system of 100% for 8 hours of release, that gives you then enough time to pump water back up again when electricity is cheap, that we'll be able to generate 9.9 thousand megawatts, in other words 9.9 gigawatts hours every day with 5 turbines. It's Wednesday the 12th at 8 o'clock in the evening, and the temperature at the moment is 40 degrees centigrade. So here is Eastern Standard time at 19:30 on the 12th of February, Wednesday, and we can see here the top line is showing what's scheduled and as a demand and with supply. So at the moment Queensland has excess of scheduled electricity, mainly in the form of voltaics and a small amount of wind. Meanwhile in New South Wales, the two are basically matching up with one another, supply and demand. But in South Australia, it's so hot, heat wave which has only been experienced in Adelaide, in South Australia, the demand is 3,263 megawatts, but supply is only 2,571, most of which at the moment is voltaics and a small amount of wind. So we've got two interconnectors between Queensland and New South Wales, and the negative indicates, normally the positive means they're going north, the negative means it's going south. So 9 is going south at that point, and 487 is also going south from Queensland. From New South Wales, the electricity normally is going upwards to the north, the negative means it's going south, and so 505 is going south. And meanwhile into South Australia, 628 is going into South Australia. That's probably using the Murray link, and this is showing this one is fully occupied at 63. The red indicates that it's 100% utilisation. And from Tasmania, where there's an excess of solar and wind over demand, electricity being exported into Victoria. So it's basically all flowing into South Australia at the moment. Let's look at the demand and price. This is South Australia. That's pre-dispatch. Now let's look at the actual dispatch. So we can see that we can looking backwards in time. So this is the current moment. The current moment the demand is 3,346 megawatts, and the price is 17,500 per megawatt hour. Prior to that, the price was 356 megawatt hour, and demand was 2,900 and something megawatt hours. At 1,700 hours, the demand was down to 1,900 megawatts, and the price was 114. And in the middle of the day, at 7 a.m, the price is 151. Compare that with yesterday at 7 a.m, the price was 64, and then 10 o'clock was 35. That's 10 o'clock in the morning yesterday, and 12 noon yesterday the price was 69, and then at 2 o'clock the price went up to $156 a megawatt, and then at 17 hours the price was 141, and at 18 hours 20 the price was 291, and this price, the price went up to 4,900 when the demand reached 2,934 megawatts. So we've got the normal pattern that during the day the electricity is cheaper, and at night time the electricity is more expensive. But because of the extremely hot weather we're having, the demand is really up in the evening, because Adelaide people now use refrigerative electrical air conditioning. If we look at the fuel mix for South Australia, that's the current. If we look at the last 24 hours, when we go back in time, we can see that at 5 o'clock in the morning on the 10th, I'll bring this up so you can see the full thing. We were relying basically 92% on wind. At 6 o'clock in the morning, some batteries were being used to give it electricity and gas. At 8 AM, the wind is now 64% and the solar's 26%. And in the middle of the day, there's less demand, but solar is taking over the main. But interestingly, at 12 o'clock, some batteries are releasing their supply of energy. And then we're at 2 o'clock on the 10th. And here we are at 18 hours on the 10th. And we can see that gas is now becoming an important part of our supply. And it's 19 hours on the 10th, 41% of the energy is coming from gas. And the other major one is wind, followed by batteries. And then come 20 hours on the 10th, we're basically running on wind and gas. And so we then come to 10 o'clock and it's all wind and some gas. And then in the middle of the night, we're relying entirely upon wind. So, if we're going to be making money from using arbitrage or trading, we're going to want to buy in when the electricity is cheap, which is here on the 11th in the daytime when the price is 22, and at night sell it when the price was 161. So we'll use those figures in our example. So here I have expanded the worksheet for our example of what we could do in South Australia, where the pumped hydro dams in this closed loop are taking the same amount of water as in Happy Valley in Adelaide of 11.5 gigalitres of water, and that converts into 11,500 megalitres or 11,500 mega kilograms. There should be kilograms there. Which comes out to this very large number, and in 8 hours there's 28,800 seconds, so in every second 399,306 kilograms of water is flowing down a height of 395 metres and generating 1,237.8 megawatts of electricity over 8 hours. So that comes to 9,900 megawatt hours in one day. And to do this we have 5 turbines of 250. The price was $22 on the 11th in the cheap period, and we've chosen 161, but we saw it in some cases went up to the thousands. But we'll just take that number, which means the average, the margin price difference is 139, and so at the sale price of 139, it means we're making $1,337,000 for 1 day's buying and selling electricity, which would come out at $500 million in a year. And pumped hydro normally lasts for 100 years, so on those figures, in 50 years we would make $25 billion, and over 100 years it come to $50 billion. If we're looking for something smaller, let's compare it with the Presenzano in Italy, where the 2 dams are at 6 gigalitres, so we change the number here to 6. And 8 hours means we don't need 5 turbines, we only need 3. So it's a smaller power station, and with those figures we would make just under $1 million a day and $250 million in a year, and 13 billion in 50 years, or 26 billion in 100 years. If we wanted to choose even smaller reservoirs, such as the Hope Valley in Highbury, where the volume of the water is 2.8 gigalitres, then we'd only need just over 1 turbine. The reality is that the requirement for atomic reactors is the atomic reactors be at 1 gigabyte capacity. So probably the Happy Valley example of 11.5 with 5 turbines is what we should be considering in South Australia, because this would give us a 1.3 gigawatt power station, equivalent to the 1 gigawatt power station that the Liberal Party is promising at the current election for atomic reactors. But this is the kind of money that at $25 billion we could make from this power station called Mount Brown. This is the McLaren Vale treated water storage built by the SA Water, and the key features here are that the project is 600 megalitres, which is 0.6 of a gigalitre, built in June 2020 for a cost of $7.4 million. If we did something 10 times bigger, in other words for $74 million, we would end up with 6 gigalitres of water, which is the kind of size we need for our Mount Brown pumped hydro energy storage. And you need 2 of these, one at the bottom of the hill and one at the top of the hill. Each would cost $74 million in 2020 dollars. Here we're looking at this site called Mount Brown, which has got this head of 395 metres, and it's using penstock running down the outside of the escarpment, so that there's not much tunnelling going on, and the water can run from the upper dam probably by gravity around the slope to the top of the penstock. And we saw that McLaren Vale Turkey's Nest, built by SA Water, has a volume of 600 megalitres, or 0.6 of a gigalitre, and one of those turkey nests cost in 2024 dollars, $8.84 million. Now if we put one of these at the top and one at the bottom of the hill, that's $17 million and $24. And at that point we got 0.6 of a gigalitre, and if we're running for 8 hours using those figures of the other day of $22 and $161 as the upper price, we would make $26 million every year from the sale of our electricity. Now, a quarter of a turbine is not a very big system, so if we made this 5 times bigger, so that the volume was 3 gigalitres, then we'd need 1.29 turbines. Let's make it 10 times the size of McLaren. And now we are at 6 gigalitres of water. 6 gigalitres of water is just on 3 turbines, which has given us 0.75 gigawatts, and we would earn $262 million a year, and the cost of the dams, using McLaren Vale example, would be $176 million in 2024. So if we multiply the turbines are probably a similar cost, and the penstock and so on, we can see that we probably could pay for this in about 4 years of running the system. So using Turkey's Nest similar to McLaren Vale and running the water down the outside of the slope, it suggested that this system in 50 years would earn $13 billion, and we probably would pay for it in the first 4 or 5 years of production. This is the McLaren Vale water treatment pond dam, which is the Turkey's Nest, as we can see, and we know the cost of this, and it was built recently and has the advantage that we can then use the idea for our own pumped hydro system. You can see, in fact, there are 3 ponds here at McLaren Vale, and this is south of Adelaide, and it shows here the yellow lines of the power distribution lines, some of which are owned by one of the companies which was the successor for the nationalised Electricity Trust of South Australia. We're showing here the Torrens Island battery and the famous Hornsdale battery. The blue lines are the natural gas, and the yellow lines we know is electricity, and just up here is the Bolivar Sewage Works, which is where biogas could be created if we wanted to use a substitute to natural gas. But our focus here is on pumped hydro, and the key thing is to position this where it's close to the power lines, close to the source of generation of electricity. And at the moment there's been a great concentration in this area here, as shown by Hornsdale, of wind and solar panels and usages for it. So over here the South Australian government is building a desalination plant which requires water and electricity to produce clean water, drinking water for the mine at Olympic Dam for BHP using seawater, and this would need to run 24 hours a day. So when the sun's not shining and the wind's not blowing, the desalination plant will still need electricity, and so that's where pumped hydro of a sufficient size would enable that to continue functioning. The other one, of course, is Whyalla, and the desire to have electric arc furnaces, and these electric arc furnaces will require electricity 24 hours a day. And then there's a discussion of green hydrogen. Produce green hydrogen would involve the production of hydrogen 24 hours a day. When the sun's not shining, the wind's not blowing, you'd need to have a battery backup, and it's suggested that the pumped hydro is the ideal, cheap, effective way of doing that. The other thing is, over here at Port Augusta, the Liberal, and we're in the middle of having election time, this is where there used to be a coal-fired power station using brown coal from along this line up here from Lee Creek. There's a rubber line just there, as you can see. And it's proposed to have perhaps we haven't actually said what the size of the atomic reactor is, maybe half a gigawatt or maybe 1 gigawatt of nuclear energy. The orange line is where BHP has got private power lines in parallel to the other power lines. These are private power lines. And what we've got is that big companies like BHP are not using the normal grid. And of course the other one is probably here, the Hornsdale battery is actually being used, and the wind farm around it's being used to supply the people in Canberra. The ACT electricity supply is not part of the other AEMO that we've been looking at. But let's get back to our friends at Mount Brown. It's moving closer. This particular image, the size of the area here is actually the same size and area as the one at Happy Valley, which is 11.5 gigalitres. We're perhaps looking for something smaller. And so, but what we're looking at is an upper dam and a lower dam connected by pipes. And if we look at the pipes, so this is where the penstock is. That's the penstock there. And so the water is being stored in this upper dam, and the water is being run down the slope, and this points a power station. Now the theory is that because this is closed loop, the water's going to be used over and again and again. So whilst there's no water here, because it's so dry, we actually are just nearby to the Mannum to Whyalla pipeline, which is carrying water from the Murray to Whyalla, and this water will be used once and once only, and used over and over again. Now because the area is dry, if there be some evaporation, it's suggested that the covering of the water, similar to what's being done by SA Water in its various facilities, is what we should be doing here as well. The ideal company to do this is actually SA Water. It currently produces electricity, it currently builds dams, it currently pumps water around. So it would be a logical extension to extend the remit of SA Water, which is actually owned by the South Australian government. That SA Water should actually build this pumped hydro system. Now if we come down, we get a view of the facility at a lower level. So that's what it looked like if we were to run pumped hydro electricity storage in the area where the electricity is produced by wind from all the turbines on these hills and from the solar panels, and where there's a huge market for the electricity with the industry up to Olympic Dam, the new desalination plant, which is going to be south of Whyalla, and the electric arc furnace at Whyalla, and that SA Water is the logical entity which the South Australian government should change the remit so that it actually expands its current activity in the generation of electricity.